Today we're going to be taking a look at some different formulas that we can use to figure measurements for things like arc length and area of a circle, and maybe not the whole circle, but just like a part of the circle, what's called a sector, or if you think of like a piece of pizza. I'm trying to find out how big that piece of pizza is. So first thought is our arc length, the circular distance around an arc. So we have done arc measure before, where that is, let's say for instance, in the circle, this angle is 60 degrees, and we would say the measure of the arc is also 60 degrees. So we want to find the length. So I want to see, like for instance, if I put a piece of string going from point to point, and I were to straighten that out and put that on a ruler, I want to see how long that is. So if I want to find the length of that arc, well, if I wanted to find the length of the whole circle going all the way around, that would be like saying I want to find the circumference. So we want to keep that in mind. Okay, so maybe what is the circumference? That's a good starting point. So we know circumference is either 2 pi r, or we could say pi times diameter. Since they've told us the radius is 10, I know if my radius is 10, then my diameter is going to be 20. So we could either say it's going to be about 20 pi, or if we round, we could say maybe about 62.83 centimeters. But that's the distance going all the way around the circle. I don't want it going all the way around. I just need 60 degrees of that. So I only need 60 degrees out of 360. So if I'm going to find that arc length, it's like saying I need a part of that. So out of my circumference, out of that 62.83, I only need 60 of the full 360. Okay? So if we were to plug that into your calculator, this is a great place to use a fraction template. So we could say 62.83 and then we're going to get our fraction template. Type in our 60 over 360, and we can see we get somewhere around 10.47. So I could say that our final arc length here is about 10.47 centimeters. So the distance going from here to here is about 10.47 centimeters. Okay, so that'll bring us up to an arc length formula. So our arc length formula, think about what we just did. We are going to take our circumference, so pi times diameter. We're going to multiply that by the number of degrees, and I'm going to clarify here, this is of the central angle. And we're going to divide that by 360. So that's your arc length formula. So this here, there's your arc length. So circumference times the number of degrees over 360. The degrees is your central angle. Okay, so we're going to try number 2. So the radius of the pictured circle is 36 centimeters. So I'm going to stop, draw that in. Radius goes from the center to the edge. That's your radius that we have. And it says angle ABC is 60. Notice angle ABC is an inscribed angle. So going back to what we have previously learned, an inscribed angle is half of the arc. So this measure of the arc here then has to be 120 degrees. Okay, we need to find the arc length. We just found the measure. The measure is 120. We need to find the arc length. So we said in order to do that, I need to know the central angle. So knowing that arc is 120, I can tell you the central angle is 120. Okay, so now we're going to find our arc length. And it does say it wants it in exact, meaning I'm probably not going to press the pi button here. All right, so we have pi times our diameter. So our radius is 36, meaning our diameter is 72. And then we're going to multiply that by 120 over 360. Okay, so again, fraction template's great here. We're plugging in all of our numbers. The only number that we're not pressing is pi because it's exact. And when we do this, we get an exact arc length of about 24 pi, and we could say units since it's a linear measurement. All right. Number 3, an arc of degree measure 60 has an arc length of 5 pi. Notice they've given us the arc length this time. What's the radius of the circle? Okay, so let's think of our formula. So you have your arc length is equal to circumference, so pi times diameter, and then times our degree over 360. Okay, so they've given us the arc length of 5 pi. We don't know the radius, so I'm going to leave this right now as pi times diameter. And we know it has a degree measure of 60, so we have 60 over 360. Okay, so first things first, I could look at this and notice that my pi's are going to divide out. That's good. I could take 60 over 360 and reduce that, and that's going to reduce to 1/6, and now I have times my diameter. So to get rid of that 1/6, think multiply by the reciprocal. So multiply over here by that 6. So now we know our diameter is 30, but I only want the radius, so I need half of that, so I can say your radius is 15 centimeters. So that's a different way to use your arc length formula, solving for a different variable versus just the arc length. Okay. Vocab word, sector. I mentioned that in the beginning. A sector is, if we were to look at this picture over here, that's that darkened in area right here. That's your sector. That's like that piece of pizza. Okay, so when we're talking about the area of a sector on our next page, we're basically saying like the area of that wedge of the circle. And we need to have a formula for this. So think about how we did our last one with arc length. We basically said I'm going to find only a certain number of degrees of the circle. So same thing here. To find the area of this, well, I would be saying I want to find the area of the circle, so pi r squared. But I only want a certain number of degrees. So same thing, we're going to have the number of degrees, and again, of the central angle. Okay, and we're going to divide that by 360. So we're going to try this. I'm going to draw us a picture here for number 4. Always a good idea to draw yourself a picture if one is not provided. So circle O, meaning O is your center point, has a minor arc of less than 180. It says of AB. So here's AB, we're talking minor arc. And an angle measure of 60. So our central angle measure 60. Sector AOB. So the sector, again, that's that wedge that we're looking at there. It says it has an area of 24 pi. What is the radius? So we don't know the radius. Okay, so we have our formula up above. We know the area, so I'm going to replace that with 24 pi. It says it should be equal to pi times radius squared. We don't know what the radius is, so I'm leaving that r. And then we're going to multiply that by the number of degrees of our central angle over 360. Okay, so again, like in our last one, pi's would divide out. In our last one, we reduced that 60 over 360 to make our calculations a little bit easier. So we said that that reduces to 1 over 6, and we have r squared. And I'm trying to get that r squared by itself. So I'm going to multiply again by the reciprocal. Multiply each side then by 6. So that's going to give us 144 is equal to r squared. And if I want to find r, I'm going to square root each side. And we're going to find r is 12. Keep in mind you always get a positive and a negative answer, but again, I'm looking for a distance, so I'm only going to keep that positive answer of r. So moving on. So we have 2 circles. They're shown below with sectors defined by central angles of 60. Notice they have the same angle measure. Their radii are different. One thing to keep in mind, all circles are similar. I can do that. I can prove that to you by saying if I did transformations, I could take this circle on the left-hand side and I could translate it to the right so that my center points match up. And then all I need to do is dilate, let's say this guy, so that 5 is now the same size as 8, and we've just proven them similar because we've done a dilation transformation. So keep that in mind. All circles are similar. We have to calculate the arc length for both of the sectors, and then we're going to find what's the ratio of the arc length to the radius. And we're going to keep it all in terms of pi and in simplest forms, meaning reduce any fractions. All right, anytime we want to reduce fractions, remember on your Inspire menu, 2, and then press enter. That is going to reduce your fractions for you. Okay, so our arc length. So for this one, again, we want to think circumference. So we're going to have our diameter, which would be 10. So I could say 10 pi, that's our circumference. But now I only need 60 degrees of that 360. We're going to reduce, and we're going to keep this in terms of pi. So we can plug this all into our calculator, keep in mind, except for the pi. So if we did, again, what I would do is I would go back, I'd get my fraction template, and when you're multiplying this, we should have 10. So we got our fraction template and did 60 divided by 360, and that gave us a decimal, but I want it in simplest form, so I did that menu 2, and that brought us up to 5/3. So if I go back, I could write this in simplest forms. I would have 5, don't forget your pi, so your pi is included in the numerator, divided by 3. So I have 5 pi over 3 on this. Okay, now we want to make the ratio of the arc length. Notice we're symbolizing the arc length with S. So the ratio of the arc length over the radius. Okay, I'm going to do this work over here. So I have 5 pi over 3 divided by the radius, and the radius is 5. Okay, I can put that 5 over 1. Then if we think of dividing fraction properties, keep, change, change. Keep the first fraction. Change to multiply. Change or flip your second fraction. So that allows us to multiply these through. The 5's reduce out. And notice what we're left with. We're left with the value of pi over 3. Okay. We're going to do the same thing over here for the other circle. So our arc length, so we need our circumference. So pi times diameter, or 16 pi. And then again, times the number of degrees over 360. Okay, so again, simplest radical form, I plug this all into my calculator except for pi. Menu 2 will reduce your fraction. And when you're done reducing, you get 8 over 3, and keep in mind you want to attach that pi to the numerator. So when we're finding this ratio, again, we're going to do the same thing that we did over there. So I have 8 pi over 3 for my arc length, divided by the radius, and the radius is 8. Okay, so again, keep, change, change. Or we can also think copy, change, flip. Okay, the 8's reduce out. So again, notice what I'm left with. I'm left with pi over 3. Interesting. Okay, so both cases, the ratio of the arc lengths to the radius is the same. Remember, let's go back. We said that those circles were similar to each other. They had the same kind of a scale factor. So it says it only depends on how much we have rotated because the two circles are similar. This gives rise to the definition of a radian rotation. So we've seen that radian thing appear on our calculator, that RAD measurement. We're going to start to talk about radians. So a radian rotation of arc length S about a circle whose radius is R is given by this formula. So theta equals S over R, theta being the angle measure. So this is like saying my angle measure is equal to the arc length divided by the radius. So we're going to try that formula. Okay, we've seen this picture earlier, and it says the radius of the picture is 36 centimeters and our angle is 60, and we said so this arc must be 120, and we went through and since it means our central angle is 120, and we had a radius on this of 36, so I'm going to label my radius. And it says, what's the radian measure of the central angle? All right, well, we had that formula, theta is equal to S over R. S being our arc length. All right, we did that at the beginning of the note. So we know our arc length is our circumference. We said pi times diameter, and then we had the number of degrees of our central angle over 360. Okay, well, if we calculate this out, so we have 72 pi, and then we have our central angle over 360. So if we keep this in terms of pi, just to make our life a little bit easier, we can find the arc length here is 24 pi. Okay, so let's go to this formula. So we're looking for theta, but in terms of a radian measure. So theta is S over R, so our arc length, 24 pi, divided by our radius of 36. Okay, so in your calculator, I would, again, type in that fraction, 24 divided by 36, and do menu 2 to reduce it. And what you're going to see is you're going to get 2/3. So it's going to show up like 2/3 pi. Now, normally you won't see it written this way. Normally you see that pi in the numerator, and you're going to get something that looks like 2 pi over 3. So what we've just done is found your central angle in radian units. So we know that we had either theta was 120 degrees, or we could say theta is 2 pi over 3 radians. Okay, which brings us to a little bit of a conversion. And this is on your formula sheet that you will have on the Regents exam, where it tells you 1 radian is 180 over pi degrees, or 1 degree is pi over 180 radians. So if I know that, that would almost give us a quicker conversion to answer that question up above. They just wanted to know what the central angle was in radian measure. Well, if I already have degrees of 120 and I want it to go to radian measure, I need to multiply this by pi over 180. Okay, so same thing like we did before. In your calculator, I would type in 120 over 180, and then I would go menu 2, enter, and that will reduce that for you. And what that's going to do is that's going to give you a value on your calculator. It's going to say 2/3. Don't forget you have pi still. Okay, or you could write it out and say 2 pi over 3, which is, again, more of what you're going to see. Okay, so that's an introduction into arc length and into our radian conversion. We're going to be doing more of this in class. Hope you guys have a great day.